Welcome into Calculus 3. Today we're going to go over double integration just with Cartesian coordinates, and I'll explain that in a second. Right, so this is just going to act as a very brief intro. Reminder from Calculus 2, we did single integration, right, which was area under a curve or area between two curves, right? We could have had either one. Now that we're moving up into Calculus 3, right, if we're doing double integration, right, what we're going to be seeing is volume underneath the surface, right? So volume, surface, area and curve, volume and surface, or volume between two surfaces. So those are our possibilities. Right, now you'll notice, right, over here, if we're integrating with respect to one variable, it's very easy, right? If we're integrating with respect to x, right, we're just going to go through our integration techniques. But over here, right, we have two variables. So I want us to also think back to what we were just doing with partial derivatives. Right, so partial derivatives, how did we deal with derivatives of many variables? Well, if I wanted to take the f sub x, or the derivative with respect to x, I treated x as the variable and y as the constant. Right, now that same technique applies over here. Right, so notice the ordering of dx and dy here matter. Right, so if I want to take the integral, right, and I have a dx first, I need to do it with respect to x, meaning I treat x as the variable and y as the constant, and then once that's done, then I can go into dy. Again, this is just serving as a very brief intro. Before we get into some examples, we'll see a few different variations, but overall, what we want to recognize is from Calculus 2, we were doing area under the curve or between two curves. Calculus 3, right, we're going to be dealing with volume, right? So it's going to be the volume between surfaces or just under a surface. Right, so a little bit more complex over here. There's different double integrations that we'll see. We'll see polar coordinates. We're not going to introduce that quite yet. And spherical coordinates once we get into triple integration. But for right now, we'll just deal with Cartesian coordinates or just x and y. So you'll see the dA representing dx, dy. And we'll go through a few different examples here. Right, so I will see you in the next part of the video. We'll do some examples. Welcome in. Let's go ahead and jump into this example. Right now, double integration, it does matter the order here, so make sure we pay attention. This is saying dy dx, meaning I'm taking the integral with respect to y first and then x. So let's go ahead. I'm treating y as the variable, x as a constant. What do we end up with? We don't touch the 3, 1, right? We haven't done anything with this yet. And now we end up with 4x squared is just a constant hanging out. Integrate y, right? Well, that's going to be a reverse power rule, y squared over 2, minus 5xy, right? That constant gets another y tacked onto it. And we are integrating between 4 and 0. And we still have not integrated with respect to x. Right, so we have to leave that there. Okay, so that's our first step. Next step, we need to evaluate y. So be careful, don't plug this in for x. We're evaluating y at 4 and 0. So we have still 3 and 1. If I plug in 4 here, I get 4 squared, 16, divided by 2, 8. Times 4, 32. X squared. Minus, plug in 4, 20x. Okay, now we'll pause here for a moment. Normally we would plug in the 0, but what happens if we plug in 0? If I plug in 0 here, I get 0 minus 0. We don't need to worry about it. Dx. Okay, so we'll pause for a second. Now what do we have? We have a normal, right, a single integral, right, or a calculus 2 type integral with some reverse power rules. So let's go ahead. We'll jump into this. So now let's integrate with respect to x. This is equal to, we have 32, and it's going to be x cubed over 3 minus, let's say, and we need to evaluate this whole thing still at the end, minus, this is going to be 20 x squared over 2, and obviously there's a simplification there, from 3 and 1. Okay. Right, so now we have some bounds. We just have to plug them in. So let's go over here and let's start. So we have 32. If I plug in 3 here, what happens? Right, 3 cubed, 27 divided by 3, 9. Let's put this as such. Minus, the 20 and the 2 will cancel out to be a 10. 10 times 3 squared, right? 10 times 3 squared, which will be 9. So that is when we plug in 3 into our function. This is our new function, our integral. Okay, so now let's plug in 1. Right, 1's a little bit easier to solve. If I plug in 1, I end up with 32 over 3. If I plug in 1, I end up with 10. Awesome. Okay, so now we just have a bunch of algebra to do. 32 times 9, 288. So this is 288 minus 90. And this is going to be minus, well, 10 is going to turn into 30 over 3. So 32 over 3 minus 30 over 3, 2/3. All right, almost there. We have 198 minus 2/3, and unfortunately, right, we got to get a common denominator of 3 here. I believe we're going to end up with 594 over 3 minus 2/3, which gives us a final answer that cannot be simplified of 592 over 3. And that is our final answer, right? Okay, so again, dy dx, we integrate with respect to y first, then x. We'll see sometimes the order, in this case we could, because they're independent, we could flip the order, it wouldn't matter here. But we do want to pay attention to this. We'll see in examples following that maybe these variables will be dependent of each other, meaning maybe y is changing with x or x with y, etc. Right, so we're going to see where this might come into a more important play. But for right now, right, integrate with respect to y, treat x as the variable. We work our way down all the way to a normal calculus 2 type integral, bunch of reverse power rules, some evaluations, and we are done. Right, so that is it for the first example. I will see you in the next one. We'll do one including dependent, right, x's and y's, and we'll see what that means. See you guys there. Welcome into our next example, right? So this one's going to be slightly different than the previous one in the sense of this is what I call dependent x and y. Right, so we can see from the question here, we're going to integrate some surface. So let's write out what the surface is. Right, so we're going to end up with some double integral. And our surface in this case is z is equal to x. See if we can get that to right. E to the negative 2y cubed. And I'm going to leave it there for a second. Now the reason why we want to do a little bit more investigation is because we notice with our bounds here, right, I think actually I have it written down there, is that our x here is dependent on our y. Right, and if you have a variable that's dependent on the other one, we need to integrate that one first. So we're going to do dx first. Again, the reason here being because x is dependent on y, x is between 0 and 3y. So we have to do this one first. And then after we do the dx, then we can do dy. Right, in this case, we're 0 to 2 for dy. Right, so again, the one that is dependent on the other must be integrated first. In this case, x is dependent on y. We must integrate x first. Okay, now we can actually just go for it. So let's go ahead, right? We're going to integrate the x. This e to the negative 2y cubed is a constant. So we end up with 2, 0, doesn't change. We're integrating only this x piece, right? So this becomes x squared over 2, we have e to the negative 2y cubed. And again, this whole thing is being evaluated between 3y and 0. We still have this dy left on the outside, right? We haven't integrated with respect to y. So we need to be careful here, right? Because we might get caught up with the y's, trying to plug it into the y's. This 3y is going into the x, right? The 3y is going into the x. So let's go ahead and now evaluate. I have 2, 0. If I plug in the 3y squared, this ends up being a 9y squared. 9y squared over 2. And we still have the e to the negative 2y cubed. Now, this is another case where if you plug in 0, you're welcome to go do the work. But if we plug in 0, right, 0 over 2 times everything, right, so 0, we don't need to really plug in the 0. It'll evaluate to 0. So now we're left with this, with our dy. And now I'm going to do the extra step of just pulling out this coefficient 9 over 2 so it looks a little bit nicer. Right, so we have 9 over 2, the integral of y squared, and we have e to the negative 2y cubed dy. And I didn't forget about the bounds, don't worry, 2 and 0, okay? So this might take a little bit of staring at, right, until we realize what we're supposed to do. Right, so pause the video, stare for a second. Okay, I'm gonna think that you're back. Right, this is going to be a u substitution problem, right? So I'm going to write it over here. We're going to set u equal to negative 2y cubed right? Which means du, let's write it here, is going to be equal to negative 6y squared dy. And now the reason I wanted to do this, right, is because when I take the derivative of u, right, du, this y squared is going to go away with a little bit of algebraic manipulation over here. I can solve for a y squared dy, right? This is really the only piece that I want. So this ends up being negative 1/6 du is equal to y squared dy. Okay, so now we can rewrite our integral, making a few replacements. So let's see what happens. We'll rewrite the integral. We have the integral. I'm going to wait on the bounds for a second. Right, we have a negative 1/6 and we have a 9 over 2. What does that simplify to? Negative 9 over, negative 9 over 12, or negative 3/4. Right? So negative 1/6 times this 9 over 2, negative 3/4. And now we can make our replacement, right? Well, the y squared dy, y squared dy is just going to be equal to negative 1/6, which we've already calculated into here, du. And then instead of writing e to the negative 2y cubed, it's now going to be e to the u. Awesome. And now this is a much easier integral to solve. So again, the process here is we have our double integration. In this case, x is dependent on y, so we have to integrate x first. Once we do that, we end up with a single variable, right, integral. So now we're back to calculus 2. We have a u substitution problem. We've simplified it. The last thing that we need to do is, because this is a definite integral, we have bounds, we can just switch them over to u bounds. So in other words, my x here was equal to 2. Right, so if x is equal to, we'll write it over here. Let's see. We'll put a little bit of a line. X was equal to 2. Right, that's my top bound. If I plug it in for u here, right, this is, or sorry, y is equal to 2, my mistake. Y is equal to 2. If I plug it in, 2 cubed, 8 times negative 2, I'm going to get 16, or negative 16. So again, if I plug in y, this is a y, is equal to 2, I get a u is equal to negative 16, so I replace the bound. And if I plug in a y is equal to 0, well, this is just going to be u is equal to 0. Right, so again, for u substitution, I've switched everything to u bounds. And now the integral of e to the u is very nice. So we have negative 3 to the 4, or negative 3/4. And here we have e to the u, will just go as e to the u, evaluated at negative 16 and 0. That might be a little bit improper, but it's fine. We end up with negative 3/4. We have e to the negative 16 minus e to the 0. Be careful. In this case, 0 does have something that it equals, right? E to the 0 is going to be 1. And this is our final answer. There's nothing else we can do with it. There's nothing else to simplify. We are done. So again, the reason why this one is different than our previous problem is because, in this case, x is dependent on y, right? So we have to integrate x first. Once we integrate x, right, we make our simplifications. We're down to a single variable integral, in which now we can go do a u substitution type problem. Okay, so we will do one more example. I will see you in the next one. Thanks. All right, last example problem, right? So we have a question that's going to pop up here. Again, we're going to do double integration, so let's set up the integral part at least. So we'll say the double integral, and we have our function. It's going to be e to the y over 3. And right now we have it listed as dA, right, from the word problem. So remember from our last example, we said if there's one variable that's dependent on the other, we have to integrate that one first. And we can see that the x here is dependent on the y. So we need to do dx first, because that is between 0 and y. And then we can do dy, which is between 0 and 2. So again, the dependent one goes first. Okay, so if we're going to integrate with respect to x, this entire thing is a constant, right? This is an easy integration for us. To 0, if we integrate with respect to x, we're going to end up with a x e to the y over 3, right, between y and 0, and we still have this as a y, dy. And now we need to evaluate by plugging in the y, right? Can't tell if my integral signs are getting better or worse. 2, 0. The y goes in now for x, right? And we don't really need to worry about this 0 again. That seems to be a common theme. If we plug in 0, we'll get 0. So we just have y e to the y over 3 dy. Okay. Now we need to stare at it for a second and go, how do I integrate this thing? Now I'm down to a single variable integral, which is great. That's good news. But how do we integrate this, right? Well, our options here are, we could go through u sub. Does u sub work? U sub doesn't work. We can investigate other options. Hopefully we arrive upon integration by parts, right? So we're going to need to use integration by parts. If you totally forgot integration by parts, I've connected a video to this. You can also watch the very end, which is what I'm going to use, is on tabular. We're going to use tabular to go through this, right? So we need to use tabular. Now tabular, I'm going to choose one of these things to be the one that I take the derivative of. So in this case, let's go ahead. I'm going to take the derivative, also known as the DI method. So one of these I will take the derivative of, and the other one I will take the integral of. Right? We want to set the one for the derivative, the one where I keep taking the derivative, it goes to 0. So y, derivative of y goes to 1. Derivative of 1 is going to go to 0. Perfect. Now the other one, which is e, right, y over 3, we want to integrate, right? Remember, we're just going to be dividing by this coefficient, which is 1/3. Dividing by 1/3 is the same as multiplying by 3. So this becomes 3 y over 3, and if we do it again, 9e to the y over 3. Right, so again, if we haven't seen this or we don't know where this is coming from, feel free to watch the end of the integration by parts video on tabular. Now these signs are changing, again from tabular, plus, minus, this one doesn't matter. Right, so our final evaluation of this integral, we still need to plug in the bounds. But again, these are being cross multiplied here. So we have a positive, we have a 3y e to the y over 3 minus 9e to the y over 3, all between, what do we have? Our bounds are still 0 and 2. Awesome. Okay, So let's go through this slowly because these aren't nice numbers to work with. So if I plug in 2, what happens? I end up with 3 times 2, 6, e to the 2/3, minus, if I plug in 2, 9e to the 2/3. Now I do need to be careful. So far when we plugged in 0, it's evaluated to 0. Well, that's not the case here, so be careful. So minus, now if I plug in 0 here, I will get 0. 0 minus 9e to the 0, 9. And let's go ahead and simplify. Right, well this will be negative 3e to the 2/3 plus 9. And I don't really like having the negative in front, so we'll just reformat it. 9e, we'll put some equal signs here. 9e, or 9 minus 3e to the 2/3. And that is it. Awesome. Right, so again, double integration, if we have a dependent variable, in this case x, we want to integrate with x first. We ended up getting an integration by parts. We used tabular. Again, feel free to watch the video. Should have a link in the corner. Once we used tabular, we rewrote it. We evaluated it 2 and 0, and then we made sure to make our simplifications. Be careful in this case, because when we plug in 0, we do actually get a value. So hopefully those 3 examples helped, right, from the first 2 parts of the video and this one. If you have any questions, feel free to ask in class or put them in the comments. See you guys.